Hi, my name is Austin Song and I'm a freshman.
And I'm John Song and I'm in 10th grade.
And we're very grateful for letting us compete in the state level competition. We learned a lot in the first one and hope we can continue learning more.
We will be submitting our project under internet applications.
We had a lot of fun editing and creating this project and we hope you enjoy. By creating this internet application, we hope to inspire students and create an educational tool to teach students robot interactivity. The idea of robots that interact with each other has been around for a while. However, the high cost for students and researchers to test such a concept has held them back. Using this application we made could make it easier for students and researchers to test and learn before entering the real playing field. There are many competitions students may enter using this application as well. Micromouse, a competition where a robot must navigate a maze in the fastest time, can be practiced online without the high cost of buying real robots. We hope that in the future, this application can be expanded and used in construction jobs. The robot may search the premise to make sure it is easy to navigate. In fact, we also have many other applications we will introduce later in this video.
Using the online Robomaze simulator is pretty simple. First, put the code that you want to use for each one of the robots on the right. And then press the download button to download the code onto each one of the robots. Then press start to start the simulation. You can use the speed slider on the right to adjust the speed at which all the robots move. You can also press the stop button to stop the simulation, and press the step button to advance all the robots one move at a time. Finally, press reset to move all the robots back to their starting locations.
We were originally inspired to create Robomaze after learning about the situation in California. One of our family friends, along with thousands of other Americans, were forced to evacuate. The frequent wildfires and the impact they have on the lives of many Americans is a serious problem. Under certain fire-related scenarios, entering inside these accidents may be extremely risky, as the original structure of the building may already be altered. This makes it difficult for first responders to locate the trapped citizens and adds unnecessary risk to firefighters entering these buildings. According to the US Fire Administration in 2020, the US lost more than 3,600 people as a result of these fire-related deaths, and over $25.6 billion in property losses from fire damage. From the year 2006 to 2020 alone, the US lost more than 1,200 firefighters while on duty. The situations in which Robomaze can be applied to is almost endless. The first application we came up with was an exploration of damaged buildings. During a fire or earthquake, damages to buildings are very dangerous to search. The earthquake could cause the building structure to weaken and make building blocks fall on people trying to enter. This is the same with fires, except with the dangerous environment that fires provide. Instead of sending firefighters, however, robots can be used to replace and negate the risk that firefighters take when they're entering buildings. The coordination of multiple robots searching a building is much safer and more efficient than humans trying to search. If you look on a picture, our internet application can directly translate to a real building using the walls as the walls of the maze. Another application we came out with is home automation improvement. When the Roomba came out in 2002, it was a huge innovation because it was able to cover the whole house and clean every room. Its technology was super simple, however. All it did was bounce off walls until it covered the whole house and came back to its original station. However, using Swarm Robotics and our internet application, we could use 4 Roombas and cover the house in a much faster time without overlapping areas that it's already covered. If you look on the picture, there's 4 Roombas that are searching its own segments so that it doesn't overlap the other robots and doesn't overlap their own places. This is much faster because multiple robots can clean much faster, and it excludes the overlapping areas so that they can clean. The possibilities are endless with these applications. Our original idea was for it to be an online teaching tool to teach students robot coordination and interactivity. However, it can be used in much other scenarios. We can apply drones to this software and use aerial searches instead of on the ground searches. Searching and monitoring patients in hospitals is another major application that this can be used in. Coordinated search and rescue is also possible using a fleet of drones to search an area.
The ease of use was our key goal when we were designing the software and framework. We used Python and JavaScript as our development language to build a framework using object-oriented programming so that other users could write their strategy by inheriting the strategy class. They can also override the function of their strategy class to implement their new algorithms. Scalability was another feature that we thought our framework should possess. Our framework made it very easy to apply this to different hardware platforms. The framework includes 8 atomic functions to override the drive functions of the motors and the sensors. The map class contains a 2D array of cells and exposes 2 APIs, getCellWall and setCellWall. This allows the user to update and query the map. These 2 functions allow you to manipulate the properties of a cell at a given coordinate by calling a cell's method setWall. The map class also provides a method of directly reading a map file by calling the readMapFromFile function. The command translator class and a wall detector class isolate the hardware operation code and the map-based algorithm code. The functions in these 2 modules are invoked by those with the same name in the mouse class. For example, goLeft in the command translator class is invoked by goLeft in a mouse class.
The Robomaze framework architecture is illustrated in the picture shown. The core component is the mouse class. This mouse class represents an agent to perform a task. It maintains the location X, Y in the maze and a local map and the direction it faces. Besides, it also contains an instance of a task loader, a motor controller, and a sensor controller. The method addTask adds 1 task to the list so that it will execute the tasks in sequence. The method run invokes start function of the task loader, and 4 functions go left, go right, go up, and go down are the general commands that control the robot. The other groups of functions can go left, can go right, can go up, and can go down tell the existence of a wall on the corresponding directions. So it runs this to see if it can go left or can go right. For self-defined hardware platforms, set motor controller and set sensor controller are used as overrides to the default controller within the robot. Navigating a city can be viewed as a graph search problem in a maze. The graph is constructed by converting a cell into a vertex. If 2 cells are connected, or rather there is no wall separating them, we add an edge between them. The depth first search, or DFS, is a fundamental graph search method. The initiative way for implementing a coordinated graph search algorithm is to make all the robots follow the rules of DFS respectively. For saving time, one robot shares the map information with the other robots so they do not necessarily have to search all the partitions, but only the partitions that they were assigned. This makes it much faster and more efficient because they can search the map in a faster time without overlapping other searches.
In terms of algorithms, I've developed a couple of preset algorithms. The 2 most basic are the wall follower algorithms. For the right wall follower, the robot first checks walls to the right, forward, and then the left. If there isn't a wall there, then the robot moves into that space. This is the same for the left wall follower, except that the order is reversed. If there are walls on all sides, then the robot moves backwards. However, note that these algorithms do not guarantee the success of exploring the entire maze, as shown in the diagram highlighted by the red. The more advanced algorithm is a coordinated depth first search. In this algorithm, the robot maintains a stack. A stack means that the last item placed in a list will be the first item taken out. The robot then checks all the areas around it and checks if there's a path there and that it has not been explored by this robot or any of the other robots. If so, the robot moves into that cell and repeats this process. If there are no more valid spots that the robot can take, the robot removes the last item in the stack and reverses that path. The robot repeats this until there are no more paths left in the stack. Note that in this maze, the robot will be able to explore the entire maze.
Robomaze can be viewed as a generic swarm robotics and coordinated navigation framework, a middleware that allows users to quickly design a map-based algorithm without distracting too much by the lower layer implementations at different platforms. The same framework has been demonstrated across multiple platforms, from network emulator to Lego EV3, to web-based simulation just like ours. By directly using such a framework, it prevents users from mixing the design and software and operation of hardware, which could be a big problem when you're trying to debug the system. When the user is not sure whether the problem comes from algorithm design or manipulating the hardware, our framework facilitates solely on examining these algorithms. The Robomaze simulator includes a web-based simulator for swarm robotics, coordinated maze discovery, where new coordinated maze navigation algorithms can be designed and tested. We have also implemented the Robomaze middleware and framework in the core network emulator and Lego Mindstorm EV3 to simulate the coordinated maze discovery with TCP/IP communications. In either of those platforms, multiple robots need to coordinate and discover the whole maze in a distributed fashion. The robots can exchange information using asynchronous UDP broadcast protocols. This will tell the other robots that they have already searched a place so that they do not have to search it again. And this will also help the robots make their own decisions, own navigation systems.
We both came up with the idea of developing a framework that would allow others to come on and develop code for the robots. I gave my brother the job of testing the program, and I did the programming. Overall, this project took us about 3 months, and I think our biggest challenge will be configuring the framework to support multiple robots. After this experience, I learned how to develop frameworks for internet applications, and my brother learned how to debug the program and find where all the errors are.
An improvement we would have added to this project is making so the robots can start anywhere on the map. We envisioned that this would work the same way, except the robots can start anywhere on the map and still explore through the whole map while sending information to the other robots. Although we placed the 4 robots in the 4 corners to represent the entries and exits of a real building, we found that not all buildings have entries and exits in the corners. And this will make it more realistic if we could place the robots anywhere and allow for more strategical placements for the robots to travel faster. I think that the biggest involvement my parents and teachers had on this project was the overwhelming support they gave us. Although me and my brother did all the work, I would like to thank my parents and teachers for the overwhelming support, guidance, and advice that they gave us. This was Robomaze, and we thank you so much for taking your time to listen to our presentation for the Georgia Student Technology Competition.
We learned a lot throughout this process, and we hope that you enjoyed our project.